We've already been doing some cross-checking of our differential equations relative to the expected circuit behavior, but I want to re-emphasize and extend those concepts in this video. These concepts are important not only to determine that the differential equation that you wrote makes sense, but also to ensure that your solution to the differential equation makes sense. There are several simple checks you can do to see if your analysis of a second-order system makes sense. The first one you can do is to check the steady-state response to a constant input. The original differential equation and the solution to the differential equation both have to agree with the expected behavior from the circuit itself. The circuit response is determined by opening circuiting capacitors and short-circuiting inductors, while the corresponding solution to the differential equation can be obtained by setting the derivatives to 0. We've already been doing this check in previous problems to make sure that the differential equation makes sense before you solve it. However, after you've solved the differential equation, you should check the value of the solution as time goes to infinity, since it's pretty easy to make errors when solving differential equations. A second easy sanity check is to see if the shape of the response agrees with your expectations relative to the damping ratio. At the very least, make sure that a system with a damping ratio greater than 1, that is, an over or critically damped system, doesn't have a response that oscillates. Also, the maximum possible overshoot for the step response of any second-order system is 100%. If your response indicates an overshoot greater than that, you've made a mistake in solving the differential equation. When checking this criteria, make sure that the initial conditions, the initial value, and the slope at the initial time are both 0. In our first example, we're given the differential equation governing a system. The output Y is a voltage in an electrical circuit, and the input U is a current. We've solved this differential equation for the case of a constant input, where the input is a 2 amp step function, and the circuit is initially relaxed. We've plotted the solution of the equation here, and we want to see if our solution makes sense. The first thing I'll check is the steady-state response. The input is constant, so as time goes to infinity, the derivatives in this equation are 0, and the equation becomes 100 y as time goes to infinity is equal to 3 times the input at infinity, which is 2 amps. Y of infinity is then 6 divided by 100, which is 0.06. That agrees with the final value of this response, so we're in good shape so far. Now let's take a look at the damping ratio from this differential equation. The natural frequency is the square root of 100, so omega n is 10 radians per second. This term here is 2 times zeta times omega n. So 40 is equal to 2 times zeta times omega n, and zeta, the damping ratio, is equal to 2. This means that the system is overdamped and the solution should not oscillate. Since the calculated response oscillates, we must have made a mistake when calculating the response. The last approach I'll introduce is relative to the sign on the damping ratio. This criteria applies only to circuits with no dependent sources. For these types of circuits, the damping ratio is always positive and any oscillations will decay with time. The natural frequency in this differential equation is always a positive number. So if the damping ratio is positive, all of the coefficients on the left-hand side of this differential equation have to have the same sign. It doesn't matter if the sign is negative or positive, since you can multiply the entire equation by -1 and consistently change the sign. The important thing is that all the terms on this side of the equation have to have the same sign. To reiterate, the damping ratio is guaranteed to be positive as long as the circuit contains only independent sources and passive elements, such as resistors, capacitors, and inductors. If the circuit contains dependent sources, the damping ratio is not necessarily negative, but it can be, meaning that the response can grow with time. Before we do more math, let's take a look at an example of a real-world system that has a response that grows with time. Systems with a negative damping ratio have responses that grow with time. They're said to be unstable. A relatively famous example of an unstable system is the Tacoma Narrows Bridge. In an instability, a dependent source has to add energy to the system in a way that reinforces the energy already stored in the system. In the case of the Tacoma Narrows Bridge, pressure oscillations caused by wind blowing across the bridge coupled with the structural vibrations of the bridge itself. The pressure oscillations caused the bridge to twist in the wind. The twisting caused the pressure oscillations to increase, which increases the twisting motion, and so on. Graphically, this is what we would see if we're driving down the bridge. Wind blows across the bridge. If the bridge twists even slightly, the force from the wind pushes the bridge in the opposite direction to the twist. Energy from a dependent source, the wind pressure is dependent upon the angle of the bridge, pushes the bridge in the direction it wants to go anyway. This system has what is called feedback. The pressure oscillations from the wind feed back to the structural vibrations. Under certain circumstances, this can cause instability. After the bridge gets pushed up, the pressure force changes direction and forces the bridge back down. This process reinforces itself to cause the oscillations to get larger and larger. Mathematically, the oscillation should go to infinity. Practically, the system will break long before that happens. Now that we've got a feeling of the process involved, let's re-enter the world of mathematical modeling and see how this affects our circuit analysis. Systems containing dependent sources can be unstable if the energy addition from the dependent source reinforces the energy already stored in the circuit. If this happens, the damping ratio can become negative, which means that the decaying exponentials we're used to seeing in the response become growing exponentials, and the system response increases exponentially without bound. This is a typical shape of an unstable second-order system response. The system response oscillates and grows with time. As time increases, the response will, at least theoretically, go to infinity. If the damping ratio is negative, there will be a sign change in the differential equation coefficients. For example, this differential equation will have an unstable response. There's a sign change between the second term and the other two terms. As an aside, instability is why we usually feed back the op-amp output to the negative input terminal. If we feed back to the positive terminal, the energy added by the dependent source, which is the op-amp, tends to cause the system to become unstable. Here's a quick example of how to use this criteria to check a differential equation. Suppose I have this circuit, and I've determined that this is the differential equation governing the circuit. The steady state response of this differential equation and the circuit agree, so from that standpoint the differential equation makes sense. However, this circuit doesn't contain any dependent sources, which means it can't be unstable and I can't have any sign changes in the differential equation coefficients. Since this term is negative and these two terms are both positive, this differential equation can't be correct. The main new concept in this video has been checking systems for stability. It's important to keep in mind that the sign change criteria for stability is appropriate only for first and second order systems. Higher order systems have different stability criteria.